Hello everyone and welcome back. Short video today because all we're going to be doing is taking stock of and reviewing all the different methods that we have learned so far to calculate and estimate the value of definite integrals. So in total, the methods on the table so far for exact calculations are to use geometry to calculate the net area being equal to the definite integral. It's also possible to use symmetry to do certain calculations, and it's also possible to use the definite integral properties to do certain calculations. Those are the only tools that we have so far to calculate definite integrals exactly. So if you're in a situation where you cannot calculate a definite integral, then the sort of last resort method is to estimate the definite integral. And the two methods that we have for estimating definite integrals are Riemann sums, and as well you can sort of estimate net area by graphing the function and counting squares, counting the net area. The goal for this video is to discuss the approach that I would use, which of those five approaches I would use at this point in the course if I was asked to calculate or estimate various definite integrals. I want to share with you my thought process for choosing a method. I want to share with you my reasoning for choosing a method, and hopefully that will help you as well as you go into today's problem set, as you go into the homework, as you go into the exams, where questions can be coming from all over the place. They're cumulative assignments, and so there will be some work for you to do in terms of figuring out what method to apply to any given problem. That's what today is about. So consider, for example, this definite integral right here. The integral of the function 4 from 2 to 5. How would I approach calculating this integral? Let's just talk about that. Because this is the integral of a constant function, we could calculate this result exactly using either geometry, using either net area, or using a definite integral property, the property for constant functions that we derived a couple of videos ago. So I would use one of those two approaches. I would probably, in my situation, I would use the constant function rule to calculate the exact value of this integral. Why? Because it'll be fast, and it'll be exact. It'll be completely accurate with no error. It's not an estimate. So because of those two big advantages, it's accurate and it's fast, I would absolutely use the constant function rule whenever possible. And since it's possible in this particular case, I would absolutely use it here. If I were faced with an integral like this one, what would I do? What approach would I use to calculate, or if I could not calculate, estimate the value of this particular integral? Well, I see, first of all, that this integral has these opposite limits of integration. And that is pointing me toward, is there a symmetry here that I can exploit? And I am seeing that there is an odd symmetry in this term x to the fifth here, but there is no odd symmetry in this back term 2. So in a situation like this one, where a portion of the integrand had a nice symmetry and the other portion did not, is I would use the difference rule, to split this into two integrals, one integral of x to the fifth power, and the other of 2. Because then the integral of x to the fifth power would be easy to calculate by odd symmetry, and the integral of 2 again is really easy, would be something I could do by constant function rule. So this is the approach that I would take. at this point of the quarter to this definite integral. I'm looking at the opposite limits. It's pointing me towards symmetry. There's a portion that's symmetric. There's another portion that's not. So I'll split off the odd portion and split off the even portion, and I'll handle each of those different pieces by different approaches as appropriate. What about this situation? Someone asked me to calculate a definite integral of the absolute value of x minus 4 as x goes from 1 to 3. Now, the first thing that I'm noticing is that we don't have opposite limits and we don't have a constant function. So the next thing that I generally check is if I graph the integrand, is there any geometry there that I can use? So going out to Desmos, here is our function x minus 4, and the problem tells us that we only care about the function as x goes from 1 to 3. So I've graphed this function, and let's have a look at the region under this graph. The region under this graph, shaded here in red, has the shape of a trapezoid, and a trapezoid is a shape that has a geometric area formula. So that is the approach that I would take to this problem. I wasn't able to use any of these really cheap methods up here, either the constant function rule or the any kind of symmetry like odd symmetry. But when I graphed this function, I did notice that the area under the graph had a geometric shape that had a nice area formula. So that's how I would find the value of this integral by using a net area calculation using the trapezoid formula. What about in this problem? In this problem, we're asked to calculate the integral from 0 to 3 of a function f of x. But we don't have a formula for f of x this time. Instead, f of x is described to us only using data. F of x is described to us using this table. So how would I approach this definite integral in this case? Because I do not have the formula for the function f of x, because I only have a table of data, there's really only one thing that I can do here. There is only one option. Given a table of data, the only thing that you have enough information to actually do is a Riemann sum calculation. And we recall that this is not going to calculate the definite integral exactly. This is just going to estimate the value of the definite integral in this case, but with the information that we're provided, an estimate is, the best that we can do. Because we don't have the formula for f of x, we do not have enough information to do anything other than a Riemann sum estimate for this definite integral. So that's probably what I would do. I would go ahead and set up that sum as I goes from the first chunk to the, in this case, the maximum number of chunks I could use is 1, 2, 3, 4, 5, 6. So maybe 6 chunks of data, a random output value chosen from the middle of the ith chunk times the width of the chunk, which in our case would be 0.5 units. And in terms of what you chose for xi star, that would depend on what kind of Riemann sum you were most fond of, where xi star is some, value out of the ith chunk, whether left or right or something else, that's up to you. That would be my approach to this problem. Given a table of data for a function, I would go with a Riemann sum estimate of the definite integral because that's basically the only thing that I can do in that situation. What about in this situation? In this situation, I'm asked to integrate from -2 to +2 the function f of t. where f of t is described using the following graph, and that graph is given in red right here. Now, once again, the first thing that I sort of notice are these opposite limits of integration. The one on the bottom is -2, the one on the top is +2. So the first sort of question I'm asking myself is there any symmetry involved in this problem? And it looks like there might be a little bit of symmetry, but I would say not quite, right? It looks almost like it has odd symmetry, but there is an imbalance between the left end and the right end. For example, this right end at x equals 2, you're all the way up here at 3, but at this left end at -2, you're only down here at -1.5. So this is not quite odd symmetry. So, barring the ability to use symmetry, and because I only have the graph of the function, once again, I would approach this using probably net area. But if I look at the net area between the graph and the, in this case, t-axis, I can see that the shapes that are being formed are unfortunately not geometric shapes that we have area for. So in this case, given the graph, but not given nice geometric regions formed between the graph and the t-axis, in this case, I would probably be forced to default to an estimate here as well. I would probably, because I have the graph here, do a net area estimate by counting squares. I can see, for example, in this picture that on the right half of the graph, between 0 and 2 on the t-axis, I have one full square, looks like another full square formed by these two pieces, a little bit more than half a square, and a little corner right here. So in total, I would estimate that the positive net area of this right region is maybe somewhere around 2.7 just by counting squares. This is almost one full square here. This is a little bit less than half a square. And then this little piece here, I might say that this is somewhere around 1.5 squares between the graph and the t-axis in this region. And this would be ascribed a negative value because it is below the t-axis. So I would estimate that the net area is probably somewhere in the ballpark of 1.2 units, but that would be an estimate because this graph is not geometric, so I cannot calculate the exact net area using geometric formulas. An estimate would probably be the best that I could do here. Let's discuss how I'd approach this problem. I have the integral from 1 to 3 of t cubed dt. So in this case, my limits are not opposites, so symmetry is not on the table. I don't really have any good definite integral properties that apply to a situation like this one. Let's go ahead and look at the graph of t cubed to see if any geometry is at play. So here is the graph of t cubed and the region underneath t cubed as t goes from 1 at the lowest to 3 at the highest. And I see that because this region has this sort of wing-shaped curved top, that curved top gives us a shape that does not have a good geometric area formula associated with it. So that blocks my ability to calculate this definite integral by geometrically calculating the net area. Once again, I seem to be out of ways to calculate the exact value of this definite integral using either properties, symmetry, or geometry. So I would be forced to do a Riemann sum estimate or a net area estimate. Given the choice, I, Sam, would probably choose a Riemann sum estimate. Why would I prefer a Riemann sum estimate over counting squares? Just because, in my opinion, it's easier when you're doing Riemann sums to get an accurate result. Because when you're eyeballing the answer, it's a really loose process, and there may be a lot of error in your estimate from the graph. So I would go ahead and set up a Riemann sum. I goes from 1 to some n value of the function random evaluated at some random x value in each chunk times the delta x, the width of each chunk. But because I am given the formula for my function instead of a table of data, it would be up to me what size delta t I should use. It would be up to me how much data I wanted to collect, how much information I wanted to put into a table that I construct. That would totally be my decision. There are sort of pros and cons. Big delta T has the advantage of being fast, but the accuracy is going to be low if your delta T is big. On the other hand, if your delta T is small, that's going to require a lot of calculations, a lot of work, a big table. But if your delta T is small, then you get higher accuracy. So it's really up to you. When you have an actual function as opposed to a table, you get to create the table for yourself, and you get to decide how to space the data points in your table, whether to space them, far apart for fast calculation with low accuracy, or whether to space them, close together for a long calculation with high accuracy. It's sort of your judgment call. Now, for the last exercise, just to tell you how I personally would approach an exercise, someone like that looks something like this. Someone gives me the integral from -2 to 5 of f of x dx, and the function f of x here is piecewise. The function f of x is linear between these two x values, and the function is constant between these two x values. Now, how I would approach this problem is I would use what we're calling the pit stop rule to split this integral into two portions, one from x equals -2 to x equals 3, that first piece, and the other from x equals 3 to x equals 5, that second piece. I would probably do the integral of the first piece can be done by graphing. I think this is another situation where you will end up with something that's triangular or trapezoidal when you graph the function. That's usually what happens when you're graphing a straight line. And the integral of the second piece, which is this function 4, this is a constant function, so this can be calculated using the constant function rule. So there you have it. Here are 7 examples of different definite integral problems that I would solve in different ways. Hopefully my sharing my reasoning with you will help you in today's problem set as you decide for yourself how to approach calculating integrals of various kinds.